So we have here a concurrent force system, and what that means is that all our forces are effectively passing through a different point. And what we're going to do here is to find the total sum of our moment, as well as to find the line of action and its perpendicular distance. Now you notice that we have this point P right there, and that's going to serve as our reference point as well as our pivot. That's where our forces will be acting. So to do my analysis, I like to use a table method because it does simplify things a whole lot, and I'm sure you will understand everything that I will do from start to finish. And the table method here, it will contribute significantly to that. So I'm going to create a table now and we can start our calculations. Right, so this here is our table, and what we're going to do is just to ensure that we understand what each column represents. So to the left we'll have all our forces recorded there, and let's say this is our horizontal component, so that's HC for horizontal components. VC will be for our vertical components, and we'll have M, and I'm just gonna put HC here, and that's for the moment of our horizontal components about the point P. You will see what that is in a second, and I'll then put another M and VC right there, moments of our vertical components about point P there. So what we'll do then is start our calculations and just work this through from start to finish to give you a full understanding here. Now there are some conventions that will remain the same. So for example, if we talk about the sum, so I'm just writing this here in top right corner, the sum of the moment, then what we expect is that this system will be in equilibrium. And what that means is we're going to have to take one turn, so let's say our clockwise turn, to be positive. So therefore our counterclockwise turn should be negative. Let's say we also do the sum of our vertical forces, so that's our vertical force component would be equal to 0 as well. And what that means to us is the sum of our upward forces should be equal to the sum of our downward forces. And we're taking upward forces to be positive, downward forces to be negative. And then finally our sum of the horizontal components, where we're taking forces going to the left to be negative, forces going to the right to be positive. So those are our three equilibrium equations that we will use. Now the last bit of rule of thumb that you need to recall is that our horizontal components will be done using the method force, cos, then the angle, and vertical components will be done using force, sin, and then the angle. So let's get the calculations done now. So I'm going to start off with the 10 kilonewtons. So right here I'll put 10 kilonewtons in that force column, and for the horizontal force component, because it's going to the left right away, I know that this will be negative, so I can jot down that negative because it's gonna go to the left. And we'll use the structure that we have up here right there. So it's the force, which is 10 kilonewtons, and then cos our angle is 40 degrees. So we have then negative 10 cos 40, and that will give us negative 7.66. And that's kilonewtons. And we will do the same thing for the vertical component, but because it's going up for the vertical component, this will be positive. So what we'll have then is just 10, and that's positive, and it will be sin 40. And we'll just put that in the calculator, final answer. So that's 6.43 kilonewtons. Now it would be a bit better in terms of flow if we do all the force components first and then we work out the sum of the moments after. So let's just carry on with the force components. So the next force that we're going to look at is that 8 kilonewtons right there, and we can see it's going in the same direction, up and to the left, and we have an angle there of 30 degrees. So let's analyze that one. So that's the 8 kilonewtons. So our horizontal component now is going to be negative. So what we'll end up with here is negative 8 and cos 30. And putting that in our calculator, that's going to give us negative 6.93. So that's negative 6.93 kilonewtons. And we do the same thing now with the vertical component. So that's just going to be 8. 8's in 30. And putting that in the calculator, that's just 4 kilonewtons. Now let's go to the other two. So we have that 7 kilonewtons there. So 7 kilonewtons. And what we have there is that force is just going to the left. So it's not going up, it's not going down, it's just going to the left. So we don't need to evaluate any force component for that one. So it's just a horizontal force going to the left. So that will just be negative 7 kilonewton. And for the vertical component, because we know it's not going up or down, then that's just 0. Now for the final force, we have that 12 kilonewtons that's going downward. And it's going to be something similar that we do here, where this force, it won't have any horizontal component and it's just going down, so it will just be a negative 12. So let me just scroll down to get some space for that. So that one is just 12 kilonewtons. I'm just writing that down for the force. It's got 0 for the horizontal component, and because it's going down, then it's just negative 12 kilonewtons there. Now the last thing that we need to do here for this column is just to sum all these force components. So for our horizontal components, when we sum these up, what we have is negative 21.59 kilonewtons. And for the vertical components, what we have here is negative 1.57 kilonewtons. So that would be the sum of the components. Now remember, what we're after is actually the sum of the moments about point P. So we are now going to evaluate those moments about point P using our components. So let's go back up and get a better view here. Okay, so let's analyze the moments now, and I'm just going to clear the screen partially at the top so you can see exactly what's happening. So if we start with the moment of the horizontal forces about P, let's start with the 10 kilonewtons there. So we have this 10 kilonewtons, and I'm just going to circle that on the diagram itself so you follow. So that's the 10 kilonewtons we're looking at there. And what we're looking at is how this force will impact right here through that point P, in terms of whether it will cause a clockwise rotation or a counterclockwise rotation. So what we need to understand first of all is what's the force component. Now what you will realize here is that this 10 kilonewtons, I'm just going to highlight the point right here, it acts right there at that point, that is 3 meters away from point P. And it's very important for you to also notice that that point where the 10 kilonewtons act, it is vertically, it's directly above point P, and we'll get into what that means in a second. So in terms of the horizontal component, then if I should just draw this imaginary line here that's representing the horizontal force, that negative 7.66, when we do the moment, which is our force multiplied by our perpendicular distance, the distance here, it must be perpendicular to the horizontal force. So we will then use what we got for the horizontal force component, which was negative 7.66, and we just need to multiply that now by the perpendicular distance, which is 3. And when we work that out, that gives us negative 22.98. And because it's moments, then this will be kilonewton meter for our unit. So that's the horizontal components there we use to find the moment about point P. Now for that same force, let's analyze it in terms of the vertical component now. So let me just clear this bit. So for the vertical component, of course, if the force is acting here, then its vertical component would be going like that. And it would be at 180 degrees or directly in line with that 3 meters. So what that means is in terms of the perpendicular distance, that perpendicular distance would actually be 0. So therefore, in terms of the moments here for that, what we would end up with is 6.43 but multiplied by 0. So in terms of the vertical component for that moment, it's going to be 0. And again, it's for you to just draw almost a right angle triangle there where you have one like that, and that's the horizontal component bit, that's the vertical component bit. And for moment, remember, it's force multiplied by perpendicular distance. So because the vertical component doesn't have any perpendicular distance, that's why it's 0. Just want to emphasize that. So let's do it again now, but this time for the 8 kilonewtons. So let me just clear this. So for the 8 kilonewtons, let's see. So this is where the force is acting right there. It's 1 meter directly across from that point P. So we can say that it's horizontally in line with that point P. So if we were to draw its vertical component, we would have something like that. And then the horizontal component would just be overlapping that yellow line for the 1 meter. Okay, so let's do the horizontal component first. And for that, because again, it's directly in line with that 1 meter line there, it's horizontally across, there will be no perpendicular distance. So what we would end up with here for this one, the 8 kilonewtons, is negative 6.93, but because our perpendicular distance is 0, then this will have no effect. So that's just 0. Now for the vertical component, what we got was 4 for our vertical component bit right here. And if we multiply that now by the perpendicular distance, which happens to be just 1, then what we have is 4 kilonewton meters for that one. And we're going to apply the same principle now. So we're going to go down to the 7 kilonewtons and see how that works. Now for the 7 kilonewtons, again, you probably can see where we have this right angle formed right there. And remember that we have no vertical force component, so at least we understand here that we're only going to end up with a horizontal moment here. Now, very importantly, you will notice here that the 7 kilonewtons, it's negative there, but I'm going to write it in here as positive, and I'll explain why that is so. So it's going to be 7 multiplied by the perpendicular distance of 2, so we end up with this being 14 kilonewton meters. The reason being, when this 7 kilonewtons act, it's going to try to rotate like that in a clockwise direction. So that moment is going to be positive, because remember we say if it's rotating clockwise, then that's positive, and if we're going counterclockwise like that, then that's negative. And if we just backpedal a little bit, you will see where that 10 kilonewtons, if I'm to just draw in again the horizontal component for that, so you will see where when I draw in the horizontal component and put that arrow there, then that's trying to rotate in this direction. I'll erase some of the scribblings in a second. So that's going counterclockwise, hence that was negative. Needed to point out that whilst I was doing it. So for the moments, the signs are dependent on how the system is being rotated, whether it's clockwise or counterclockwise. So that's what determines whether we have a positive moment or a negative moment. So back to this 7 kilonewtons, we know that the vertical component is 0, so it doesn't matter what happens here, this would just turn out to be 0. And let's go to the final one here, which is the 12 kilonewtons. Now, as you can see on the 12 kilonewtons, we have this right angle formed there with that 2 meter line. And of course, we didn't have any horizontal component. So when we do that one, we know that we'll get 0. And if you can just imagine for a second how this 12 kilonewtons would be trying to rotate the system there, hopefully you'll agree with me that that would be trying to go in a clockwise direction. So that would be 12 times 2, and it's gonna be positive, so this would be 24 kilonewton meters. Now what we need to do next is just to sum the moments, and we're going to sum both the horizontal and the vertical. So let's get some space. So what we get here is negative 8.98 kilonewton meters, and we also get 28 kilonewton meters. So for the total sum of the moments now, so we have the total sum of the moments, which would be us summing the vertical and the horizontal components together. So we have the negative 8.98, and we're going to add that with the 28 kilonewton meters. So what we end up with here is 19.02 kilonewton meters. So that gives us the total sum of the moment. Now what we would be required to do is also to find the direction of that. So hence we need to find the magnitude and the direction of the resultant force. And this is pretty much the same as we have done before, but there will be a little bit more to it. So stick around to just get this through to the end. So what we do next is find the resultant force. So for the resultant force, we are going to use the force components that we have, which is the negative 21.59 and the negative 1.57. So what we do for that is just the square root and 21.59 squared plus 1.57 squared. And in this case, it doesn't really matter if you use a negative or not, because you'll get the same answer. So what this gives us for the resultant force is 21.65. And this will be kilonewtons. So that's representing the resultant force there. Now, in terms of the angle and the line of action, for that, we need to work that out as well. So that's how we're going to get the angle and where this is going. So let's do that. So the angle is always tan inverse in this case, and we're going to do the vertical bit, which is 1.57 divided by our horizontal bit, 21.59. And notice I've just ignored the signs because we just need the magnitudes here. Now this gives 4.16 degrees. So that's representing our angle. Now what we will need finally is to work out its distance then from the pivot point, because this won't be acting through the pivot point, which is the reference point P, because if it was, then it wouldn't really have any impact. So what we do next is to work out the distance, or the perpendicular distance. Now because moment is equal to force multiplied by perpendicular distance, and what we already have is the moment, which was 19.02, so that's representing the sum of the moments, 19.02, and the force that we're having here is the resultant force, which was our 21.65. And we need now this perpendicular distance. So all we do here is just to divide our 19.02 by the 21.65. So therefore, our D for perpendicular distance is 0.88 meters. And that's representing the perpendicular distance. So all we need to do now is just represent this on the diagram, and I'm gonna just show you how to do that next. Now we have a positive moment, so just bear that in mind when we do that. So finally, let's represent this force, line of action. I'll just do a sketch actually. So things to consider: one, we have a positive moment, so we expect that when we represent our line of action, it will produce a moment that's going clockwise direction because that's positive. So our perpendicular distance then, if you can imagine, I'm just gonna draw this here. And if you can then imagine that the angle that we worked out was right, let's just use this horizontal line here as the reference. So this is where our angle would be. And the perpendicular distance, I'll just use a blue color, would be somewhat like this. Let me just zoom in a little. So this is where our perpendicular distance would be. And because our line of action with that purple mark, it needs to rotate the system clockwise, then our arrow would be pointing like that. And that would be it from start to finish. So hopefully you have found some useful tips and you understood the concept. Please share your comments if you do understand, and if the video was helpful, give it a like and subscribe to the channel if you have not done so already.